Way to deal with the lack of reproducibility in science is to conduct what we call a meta-analysis, and that will be the focus of this week's lecture. A meta-analysis is a synthesis of a number of studies that all examine the same question or hypothesis. And a key attribute of meta-analysis is a statistical analysis of the strength of evidence in the various data, either using raw data from each of the studies that's examined, or by simply taking the results and the mean values that are maybe presented in tables or figures within the analysis. And then you collect all of those results from a number of different papers and conduct a new statistical analysis performed on all of those results from the individual analyses to give you a view, an idea of what the total response is. What is there consistency in the response of the response variable to a treatment across all of these different studies. Meta-analyses are distinguished from literature reviews or literature summaries, where you may have one or a number of authors that read a whole bunch of different papers on a topic and kind of reach their own subjective interpretation on the strength of evidence, but don't actually do quantitative statistical analyses on the outcome of each one of those studies. Well, you might think it's pretty straightforward to conduct a meta-analysis. You just go out and collect all of the information from the different studies, you compute the mean of the response variable and ask, does that differ significantly from the null hypothesis or no difference? But it turns out that it's just like any study, you got to be really careful when you conduct a meta-analysis and be very, very transparent in each one of the steps that you go through. And this is especially important in meta-analyses because they can often carry more weight than a single individual study because of the fact that they're kind of viewed as a compilation of all we know about a particular question. So I'm going to go through each one of these practices individually and talk about them. So first off is a literature search. It's very important to clearly identify the source of the databases or journals that are considered. So if you're doing a search of Web of Science or Biosis, just be very clear about exactly what you have included in that. What database you use. If you're only looking at journals, what journals are those? And a really important one is what are the key words that you used when searching for literature, because that can often exclude a lot of studies that might have looked at something similar but don't match the key word or words that you used and therefore are not included in your literature database. And regarding this, Gates makes a point to not simply rely on computerized searches. I can't tell you how many times students have come in and said, well, I ran a search on the effects of logging on this species, and I only found 2 citations, so gosh, I guess there hasn't been much done. Well, in many cases, I could just off the top of my head think of half a dozen studies, and so these kinds of electronic searches can be really, really helpful, but you also have to be very careful, and it can, in many cases, exclude some very important studies. So an important thing to do is once you get a list of papers that you have selected in your search using your search criterion, is to manually check the literature cited and look for other citations in those papers that might address the same question and the same species that you're considering. You also should include the gray literature, which in most cases will not be included in online database. So this includes reports from state and federal agencies and non-governmental organizations, and it could include any kind of publication that doesn't come out in the peer-reviewed literature. Even chapters in books sometimes may not be included in these scientific databases. Another area that he suggests looking at is reviewing abstracts at scientific meetings. Oftentimes, master's and PhD students will give presentations at meetings, but either won't publish those or sometimes don't even include those chapters in their theses. So that can often give you a rich source of information about people that have worked on a particular question or species, but those results of those analyses never made it to any kind of publication. Also very important to talk to the scientists that are doing the work. They'll often know, oh yeah, somebody over at this refuge did a nice study a few years ago, but they never published it, and they have the data, they have the results. You could include it in your analysis. All you have to do is pick up the phone and give them a call, and you can often tap into a rich source of information. And one thing that we tend to do in the U.S. is be very U.S. centric and looking at only U.S. journals, only publications that we're familiar with from the U.S. And people in other countries are often thinking about the same things we are. And so looking at foreign journals, even journals that are in foreign languages that have to be translated, can often be a rich source of information that you might miss if you don't really specifically go looking for it. Next step is what type of studies are being included in the meta-analysis. And again, for all of this, transparency is the real key, because as long as you tell people what you did and how you did it, then they can go back, maybe review it and do something different, or at least they know exactly what the source of information is that's being used in the meta-analysis. So some distinctions that might be made. Are you only going to consider true experiments, manipulative experiments, or only observational studies, or both? Obviously, in our field, if you only include true experiments, that's probably going to greatly reduce the sample size for your meta-analysis. But again, just be explicit about that. Another question that we have to deal with is, is it just one species? Are you only looking at white-tailed deer? Are you looking at all deer, or all ungulates, or one species of cutthroat trout, or all trout? Again, you're going to greatly reduce your sample of studies if you focus on one species, but if that's a key important species, then that might be fine. Again, just be clear. Location, one state, the United States, the entire world. Just be explicit about what you're including in your potential source of studies that you're looking at. The methods. Are you only going to use studies that use certain types of methods, or are you going to throw all kinds of studies in there? One big issue that we deal with in natural resource studies is the idea of detectability. So we know that whenever we just do indices of abundance, go out and count the number of dove that you hear when you stand at a point, or number of fish that you see in a pool or something, that you're missing some individuals. And this is the issue of detection or detectability. We have lots of methods now to correct for individuals that might be missed when you do surveys. So are you only going to include studies that correct for detectability biases, either with mark recapture or removal, sampling or distance sampling, whatever it might be in the area that you work in. Are you going to include only studies that use those more robust methods, or are you just going to include everything, index studies and other studies? And then the other thing to be very clear about is what response variable are you going to look at? In many cases, we measure a variety of different things. We might measure abundance, we might measure survival, we might measure condition of individuals captured. Are you only going to focus on one of those, or are you interested in all variables and whether there might be some consistent response among them? Again, just be very, very clear about what you include and exclude. Gates emphasizes to present the results using point estimates with confidence intervals. So don't just take the mean of the effect size and say this is what we found and put it in a table or something. And he suggests using what are known as tree plots. And this is an example here. They aren't all going to look the same, but this is a pretty standard way of showing this. In the tree plot, the trunk is the vertical solid line here that indicates no effect, okay? Running from the top to the bottom. And then the horizontal lines are the results of each individual study. Here it's indicated by the name, maybe the name of the author or the location in this case, in the year, what sort of descriptive information you include really isn't all that important. The key thing is to put both the mean effect and the confidence interval so the reader can go down and look to see whether those confidence intervals overlap 0 or not. Another thing that Gates really emphasizes, I think it's an important one, is to put the overall pooled effect, which is the diamond at the bottom here, along with its confidence interval. And in this case, the confidence interval is so small you don't even see it sticking out beyond the sides of the diamond. So this gives you a measure of the overall pooled effect. Here they've put a dotted line all the way up beside the trunk so you can look at the various studies that fall with their confidence intervals around that pooled effect and so on. And the other thing that they do here that's neat, that I think is very helpful, is they use squares to indicate the sample size. So studies with a larger sample size have larger squares. Studies with small sample sizes have smaller squares. And in this case, this is the effects of a tuberculosis vaccine on rates of TB in various places. And so in this situation, probably having the location is important because you might find that the effects of this vaccine may be more effective in areas where there's poor nutrition or less medical availability, so that the vaccine may have more effect because maybe people are simply more likely to be exposed to tuberculosis in those regions as well. So you can see that Puerto Rico, pretty good sample size, pretty small variance, and a fairly strong effect of the tuberculosis virus, whereas right above that in Georgia or northern United States, there is an effect there, but the confidence interval overlaps 0 again. Maybe there's just not as much disease in that situation, and therefore you wouldn't expect as much of an effect. But basically, by putting all of this together, it allows the reader to look at it and make some interpretations on their own rather than just lumping it all together and putting it as one mean and standard deviation in a table, for instance. Another point Gates brings up is to investigate potential bias in the literature that you're using for your meta-analysis. Now you'd think it'd be fairly obvious, but it's very important to only consider the methods that were used when filtering studies, and obviously the question that's being asked. And don't look at the results and say, well, gosh, they found a significant effect here, but the sample size is small. I'm not going to include that because, gosh, it doesn't really, comport with what I think the results should be. And in some cases, what they do in medical studies is they have what they call blind data extraction. So they have individuals going through the literature that don't know what the hypothesis is that's being tested, that just find studies based on the question and the methods that were used and pull those into the meta-analysis. A third thing that Gates really emphasizes, and I think is a really great way to look at potential for bias in the literature that you're examining, is to use what are known as funnel plots. And I want to talk about those in more detail in the next slides. In a funnel plot, you plot the effect size on the y-axis and the sample size used in the study on the x-axis. And what you expect when you plot these two variables against one another is you're going to get a funnel-shaped distribution of the points. So at small sample sizes, because of increased sampling error, you expect more deviation of the mean effect size from the true effect size. And as you get out to larger sample sizes, it'll tend to converge on the true effect size. So the distribution of those results will narrow. A couple other things to notice in these plots is there are these converging dotted lines above and below the solid horizontal line. Solid horizontal line is the what we'll call the true effect size, the mean of all of the effect sizes that are measured. And then those dotted lines indicate the region of significance. So outside of those dotted lines, the effect size combined with sample size would be significant, and inside those dotted lines it would be non-significant. You can see the p equals 0.05 at the bottom there. So and then a final point is to plot the published studies, in other words, studies published in peer-reviewed literature, as in this case solid circles, versus the unpublished literature. That could be master's theses, PhDs that didn't get published, reports from agencies or NGOs, and perhaps abstracts that you found that have been presented at meetings, but which somebody never published, and discussions that you've had with scientists that work in this area that maybe had collected data for a few years and didn't have time to get it published, but they know what the outcome was. They can actually give you effect size and sample size and so on. So this is where really digging is important, because one of the key distinctions here in these funnel plots is the differences between the published and unpublished studies. So the more unpublished studies you can get, the better. If we look at the top graph, this is an example of a situation where the true effect size is weak and there's no reporting bias. So regardless of sample size, the information was published in the peer-reviewed literature, and you see a even distribution of the effect size around the true effect size, regardless of sample size. So there you can conclude pretty strongly that the true effect that you observed in your meta-analysis really reflects the overall effect. A second outcome might be the one in the middle here, where the true effect size again is weak, not much difference, but you have selective reporting, and this would be probably pretty common, right? So if you have a small sample size, you might be reluctant to publish that data or those results if the outcome is not significant, because, well, didn't have a big sample size, I can't be confident of this outcome, and therefore it doesn't warrant literature publication in the peer-reviewed literature. And some editors will reject if there's nothing of significance found. We've talked about this sort of significance bias. But in this situation, you see, again, a clustering of unpublished results at small sample sizes, which are non-significant. As you get out to larger sample sizes, even if it's non-significant, the authors might say, well, we got a really good data set. It doesn't show the effect as significant, but it's still worth getting out there. Maybe they spent $1 million on this study, and there's a strong push by whoever funded it to get it published. And you see at small sample sizes whether the effect size is highly negative or highly positive. Again, they're published in the peer-reviewed literature because, hey, it's significant, so must be good, and let's get it out there. And in this case, it doesn't cause any bias in your estimate of the effect size, because both positive and negative effect sizes are published. The problem, indication of a real problem, is this bottom graph here, where our true effect size might be moderate, or it might even be weak, but you get an indication of an effect size because there's a bias in the reporting. So notice here that, again, studies with high sample sizes are published kind of regardless of whether they're significant or not, but as you get to those smaller sample sizes, there's a real bias in that those that in this case have a positive deviation tend to get published. Those that either have no significance or a negative deviation are not published. And this, as I said, causes a bias in your effect size that you're putting out there, and could lead to the conclusion that, hey, there's something really going on here. Look, we've pulled all these studies together and found a strong positive effect. But that's actually due to a bias in reporting. And you'd say, well, why would this happen? Why would anybody do that? Well, if there's a situation where there's a hypothesis out there where there's a dominant paradigm, say, that's been promoted for many, many years, you might find that researchers are reluctant to publish studies with small sample sizes that are counter to that prevailing paradigm. So an example might be additive versus compensatory harvest in our field, whether fisheries or wildlife. Many fishing and wildlife hunting regulations in many states are built around the idea that harvest is compensatory. In other words, if you remove a high fraction of the population through hunting or fishing, that will lead to either greater survival of those individuals that were not harvested, or greater reproduction in those surviving individuals in the following year so that it'll compensate for the losses from hunting. And so if you were to find a study where, in fact, you didn't find compensation happening and you had a low sample size, you might say, I don't think I'll publish this, even if it's significant in the opposite direction. Because again, there's this strong prevailing attitude that, well, this is always supposed to be in this direction. Gosh, I did a kind of a small study, but I actually found significance in the opposite direction. Geez, I'm going to get really criticized or jumped on for that, so I'm just not going to put it out there. So this is the kind of bias that you're looking for when you do a funnel plot. Here's an example of a study that identified reporting bias in a meta-analysis of fluctuating asymmetry. Fluctuating asymmetry is the hypothesis that mates tend to choose other animals or individuals to mate with based on the left and right symmetry of their potential mate. And this can be measured by looking at, say, the length of the left ear to the right ear, the length of the right eye to the left eye, and so on. And the hypothesis is that those individuals that are more symmetrical, in other words, there's less difference between the left and right, will appear more attractive and will be selected more often as a mate, or might be chosen as looking more handsome or better looking, or whatever way you might measure it. And there are a number of scientists that have been looking at this, and they've been publishing a lot of their own results, and also did a meta-analysis of all of the data that have been collected on this particular hypothesis. And I'm just showing one figure from the paper by Palmer, 1999. You can take a look at it if you wish. And this shows a severe reporting bias by these individuals when they publish their own papers. So these are papers that had these individuals as co-authors, and you can see that basically nothing was published if it didn't support the idea that more asymmetrical individuals were less likely to be chosen as mates, unless it supported the hypothesis, especially at low sample sizes. And again, you can take a look at it. There is also evidence when they looked at all studies that they selectively excluded some studies in their meta-analysis in order to support the overall hypothesis that asymmetry results in lower fitness or lower choice by mates. So, again, it's not saying that these individuals are somehow being fraudulent. They may just, not recognize the biases that are inherent here. But again, when you put all these things together and come out with a meta-analysis that says, yes, this effect is strong and it's consistent, that tends to give people more confidence in that outcome. And if it's due to biased reporting, then that can cause even more problems. And that's summarized by this quote from Begg and Berlin in 1988. And they state that if publication bias is present, and if it operates in the same direction for all studies, as is likely, then meta-analysis is likely not only to produce biased summary estimates, but also to produce estimates which are apparently precise and accurate. And then this is the key, leading to conclusions which may not only be wrong, but appear convincing. So again, we tend to rely on meta-analyses to give us, the final answer to the big question of, how a particular drug affects, cancer tumors and whether they decrease over time and so on. You may think one study, yeah, that's not really that convincing, but if somebody does an analysis of all studies and says, aha, here it's showing all these studies are showing the same thing, that tends to give you more confidence. And if that result is biased, then we really get ourselves into trouble in terms of trying to understand what's really going on. So this is why looking at funnel plots, looking at bias in publications is really, really important in meta-analysis. Another point that was made is to distinguish between main and subsidiary effects. So, you may have a particular effect that you're most interested in how, say, fire affects greater sage-grouse populations, and you're mostly interested in just total number of individuals in the population before and after a fire has come through, for instance. But there may be other effects that have been measured in different studies. Maybe the sex ratio of males to females in the population, or the number of chicks that are observed with female hens at a certain time post breeding and so on. And those might be kind of subsidiary kinds of factors that can help understand this bigger effect. But the thing you have to be careful about in this case is looking at running tests on multiple response variables, very much like the Bohannon paper, where they had a crazy number, like 48, when you considered all the physiological and psychological variables that they measured. But you could even get into a situation like this example that I'm talking about, where you could easily have 10 different response variables that were measured by different people in different studies, depending on whether they put radios on females, on males, on both, followed chicks, followed nests, and so you could be looking at effect sizes from many, many response variables, and in that case, you just have to be very careful about not running into the problem of just finding an effect by chance. And there are ways of adjusting the p-values, as I talked about, as the number of response variables that you're examining increases. You can decrease the p-value such that you will reduce your chances of a type 1 error. But just something to be aware of even in these meta-analyses, because again, you want to make sure you're really being careful because of the weight that the results of a meta-analysis can carry. A final thing that Gates suggests is to perform sensitivity analyses. And there are some very formal approaches to sensitivity analysis that I won't get into here. He was talking more about sort of qualitative approaches to looking at this. And what this really comes down to is including or excluding studies in your meta-analysis based on certain criteria. And really what you're looking for is consistency in the outcome of the effect size, regardless of what studies are included or excluded. And there may be some very valid reasons for excluding studies in some cases. So if a study, you might look at the approach that was used in the overall study. So was it a before-after control impact study where you were looking at a population in an impacted area and a control area before that impact happened and after it happened, and you're comparing what happened to those two populations? Or did you just come in, say, after a fire had burned through a region where there used to be sage grouse, and now you're comparing the numbers there versus at a control site that didn't get burned. There could have been pre-existing differences there that you couldn't detect because you didn't have the before data. So you might only look at Backy studies, for instance. You could exclude unpublished or low quality studies. Low quality meaning they weren't carried on for a number of years. Maybe some of the methods that they used were methods that aren't really considered state of the art at this time. One big thing that we get into in both fish and wildlife studies is using indices of abundance versus actual corrected estimates of abundance when you are taking into account detectability. So if there are a bunch of older studies that just went out and counted fish or counted birds or mammals and didn't account for the fact that we know there were some that were missed, you might drop those out. Same thing can happen for survival studies. It used to be we just do what we call resighting. You band a bunch of birds and you see a certain number the next year, and so you just say, well, that's our estimate of survival. Well, we know now that, again, you're going to miss some of those banded individuals. There are ways of correcting for the animals that you missed, and if a study doesn't do that, you might throw it out. There are all different kinds of ways of analyzing the effect size, depending on if you're going to weight it by sample size, you're going to use the simple mean and deviation from expected, or you're going to look at kurtosis and other kinds of factors in the distribution. So again, you just want to try a number of different methods to make sure that everything is coming out consistently. And there may even be situations where you'd substitute a range of reasonable values for doubtful or missing values in order to increase your sample sizes. Again, you have to be very careful. You have to be very explicit about how and why you do this, but it could provide a more robust analysis in some situations. And again, if you include, exclude studies and finding really consistent effect sizes either way, that gives you real confidence that what you're seeing is real. If the outcome changes a lot based on the criteria, then you really got to start worrying about whether your meta-analysis is really consistent, or if we simply need more information to really be able to nail down what's going on in this particular system. We face some unique challenges in the ecological arena that might not be a problem in some other areas. So for instance, in the medical sciences, they only deal with one species, humans. And so that really simplifies things. In our case, we have millions of species out there, literally. And we could still just focus on one species if there's only one species we're really interested in. But in many cases, we want to look at a whole class of species, all ungulates or all freshwater fish or whatever it might be. And so this poses some real challenges. Do you take studies from a whole bunch of different species and lump them all together if they're all looking at the same question, the effects of fishing on fish survival or something? Or do you limit it just to individual species in which you may have very limited number of studies to pool from? We also know that things vary a lot from one region to another. If we're looking at an ungulate species, or maybe certain areas of its range where there's lots of food available, which results in higher rates of survival and reproduction, better condition, and so on. And so then if you're looking at the effects of hunting or some other factor in those different regions, you may get different results depending on habitat quality. Same thing could apply to fish, depending on whether they're cold water or warm water, and water temperature, and so on. Um, in humans, again, there's probably not that much in the way of regional differences. All people tend to be pretty well fed. Their basic human needs are met in most situations, and so there's not the strong regional variation in physiological characteristics that you might expect to see in animals in the wild. We also tend to measure a whole bunch of different response variables, as we talked about. It could be survival, it could be abundance, it could be brood size, it could be condition, length to weight ratio. In fish, for instance, could all be some measure of response to a treatment that we're looking at, whether it be fire, whether it be some habitat manipulation that we're doing, or whatever. So the question then becomes, do you combine all those variables and say, let's just look at sort of a yes-no meta-analysis? Did they find a positive or a negative response in all of, you could use all different kinds of variables in that case. Or do we want to just limit it to measures of abundance or measures of survival? Or do we want to, partition our analysis using only the same response variable? So, lots of different kinds of ways of handling that situation. Another thing that we run into, again, that is probably more unique in ecological studies is we know there's a fair amount of year-to-year variation, whether it's a wet year, whether it's a dry year, number of predators in an area from one year to the next, food availability, and so on. And so we tend to think, well, longer number of years gives us a better measure of the true response of some perturbation on a population. But, there are a lot of master studies where they can only collect data for 1 or 2 years. So does that mean you exclude all those in your meta-analysis, or do you throw them all together? Or do you do, like I talked about, a sensitivity analysis and, see if the results are consistent based on number of years? Sex and age classes, this is something that they've also dealt with in medical studies. It used to be a while ago that they would only use men in medical studies of the effects of drugs on blood pressure or whatever it might be, thinking, well, there tends to be fewer sources of variation that you need to worry about with men than with women, and they're probably responding to things in the same way. So let's just keep it simple and only include men. Well, we're finding out that often the results that we find for men don't apply to women. And so more and more now, women are being included in medical studies. Of course, you have to worry about whether they're pregnant or not, and giving drugs that might have an effect. Pre versus post menopause, maybe there's different effects. So yeah, it makes it a little more complex, but still we need to have answers on, all sex and age classes so that we know what the real effects are. And then we often find that when we get out in the field and start a study, it just happens to coincide with the worst drought that the Mojave Desert has sustained in 100 years. There's a study like that done on Mojave ground squirrels, and they were looking at habitat selection, and it was after like 3 or 4 years of severe drought. So then the question is that a general result that we can use to talk about the effects of habitat on this species in general, or is that such a unique condition that we want to exclude it? Of course, you could have the opposite, where you have periods of really wet conditions. And so again, you need to consider whether a study was done in a situation that was so different from everything else that it really justifies not including it in a meta-analysis. So obviously there's a lot more things to consider when we talk about ecological or natural resource meta-analyses than you might in, say, medical meta-analyses, but doesn't mean that we shouldn't do it. It just means it might take a little more effort, need to think a little bit harder and make sure we're considering all the different effects. And then this week you'll get to take a look at your own meta-analysis of your choice and look through the points that Gates brought up and reach your own conclusion as to whether that was a good meta-analysis or not.